So, back in grade, I'm going to guess 5, maybe 6, your teacher had you making factor trees. Your teacher probably used one of 3 or 4 different methods of doing this. Hopefully your teacher presented you with 3 or 4 and then had you choose the one that worked best for you. Because you already know how to do this, I'm not going to show you 6 kinds of ways to make factor trees. I'm going to make 1. If you don't like the way I make my factor trees, you're welcome to use the way you learned in the 5th grade. The problem, of course, is you learned this in the 5th grade and then probably didn't do it again since the 5th grade. And your teacher probably said you'll need this later, but didn't say when you would need it later. And as you have gone through year after year since the 5th grade not needing this, you will probably have forgotten a little bit. That's not your fault, it's just the way it is. So, very quickly, I'll remind you. Oops, that's a highlighter. 18. 18 breaks down into factors. What are factors, by the way? Things that fit into it? What do you mean by fit into it?
Like 6 and 3 would be a factor.
6 and 3 are factors because 18 divides by 6 and 3. Factors are any 2 things that multiply together, right? So Joseph said he would go 6 and 3. Everybody cool? What else could he have done? 9 and 2. And then, of course, your teacher said, and you have to keep factoring until you run out of factors. Yes? So 6 will break down again into 2 and 3. And 9 will break down again into 3 and 3. And we stop there because there is something special about those numbers. What is it?
Two of them are the same.
They're prime numbers. Right? No, you're jumping ahead to the next part of this. You saw GCF and LCM, and you were talking common. You're right, that's coming. But right now, we stop here because we are at prime numbers, which you will notice I've written as the very first note here. Prime numbers are, quite frankly, the most powerful numbers in our numbering system of real numbers because they are weird. They are weird because of what reason? They cannot be divided by anything but themselves and 1. They have only 2 factors, which is really easy to see when the numbers are small. Yes? What's the first prime number? No. 1 has 1 factor. 1. 3 has 2 factors, but that's not the smallest. 2. 2 is the smallest prime number. And quite frankly, the most powerful of the prime numbers. Why? Yes, 2 divided by 2 is 1, so its only factors are 1 and 2. What makes 2 the most powerful prime number?
It can be multiplied with any numbers.
Yeah, it's the only even prime number out of all the infinite prime numbers that there are. Now, here's something that is very interesting to me. You guys won't find it as interesting, but recently, using computers, of course, mathematicians have found the largest prime number. And it's like up in the billions, which is pretty mind-boggling to me that you can go that high and have no other factors except that and 1. I know, it's crazy, hey? Like, it's easy to see, okay, 5, yeah, 1 and 5, whoopee. Right? 19, oh yeah, 1 and 19, okay. 27 billion, 329 million, or whatever it is. That's crazy, but it is true.
So the higher you go, like,
the less there are, yes. Now, prime numbers are, of course, if you've seen the movie Contact, which is pretty good but weird and then had an unsatisfactory ending, you know that aliens used prime numbers to talk to us. And, of course, if you've seen the movie, it just came out. It had Hawkeye in it.
Oh, 4.
No, about aliens. I can't remember what it was called. It had Hawkeye and Amy Adamson in it. Arrival? No.
Oh, wait, no.
I can't remember.
Yeah, rival.
Where the
big round.
big round thing, yeah, and then they talked to them and they had the numbers.
With the big tentacle.
Yeah, and they learned the language. That's prime numbers. Because, of course, no matter what language you speak, numbers are numbers. This is 1 in English. Un en français. Uno en espagnol. Carplach on Alpha Centauri. Who cares? It's still 1. 1 still only has 1 factor. No matter what your numbering system is, it only has 1 factor. 2 only has 2 factors. Doesn't matter what you call it. You can only divide 2 by 1 and 2. So when aliens come, if they decide we're worth talking to, which they won't, they will exterminate us. Because why wouldn't they? We've had this discussion. I wouldn't let us risk us leaving the planet. God, no, I wouldn't even have us as slaves.
We could be the aliens, and there could be another planet.
Oh, that's what will happen. If no other civilization in the universe develops space travel, and we do, then we will just go to other planets and ruin theirs. So that's why if somebody does show up here, they will have space travel, they will have superior technology, and hopefully they will take care of the mess that we have made of this planet. A la Fifth Wave. If you haven't seen nor read Fifth Wave, bit of a spoiler alert there. Sorry. But since the whole commercial in the movie is about aliens destroying the planet, I think you knew. Where was I? Oh, prime numbers. Yes. A prime number is any number with only 2 factors. And the factors are 1 and itself. So, 2, 3, 5, 7. What's the next one? 11. Only one person said 9. I always do that. I always go 2, 3, 5, 7, then I stop. So you get in the rhythm. 2, 3, 5, 7, 9. Oh.
Why not 9?
Because 9 has another factor, 3 times 3. Then the next one is 13. Then the next one is 17. Then the next one is 19. Then the next one is 23. And then the next one is... No.
5.
No.
Oh, that's 5 times 5.
9.
No. 29. Then the next one is
31.
31. Then the next one is
37.
no.
33.
No. 37. Then the next one is
41.
41. Then the next one is
No.
oh, what about 43?
43.
You can't forget 43.
Yeah.
Now,
Now 40.
what are you noticing?
Now 48. No, 47.
You're noticing they're all odd, which we already talked about,
You gotta think about
right?
numbers.
And if they're all odd, they can't be what? What is the one odd number that they can't have at the end of it? What? Okay. I just said what is the one odd number that can't be at the end, and a bunch of kids said 2. 2 is even. And then a bunch of other people said, what's the only odd number they can't have at the end? And a bunch of people said an even number,
5.
which isn't odd.
It's 5.
5. It cannot have 5. There is no prime number except 5 that ends in 5. Why?
Because you can divide it.
Because 5 divides into all of them. Excellently done. So, yeah, 3 and 7 are... 1, 3, and 7 are your major culprits here. Yes?
Yeah.
All right. But
About 59.
there is no pattern, which is why prime numbers are even more powerful, because they are unpredictable. We have no idea what the next prime number is going to be until that computer finds it. And since we're up in the billions, it's going to be a long time. Yes. Everybody cool? Now, I know that you have been taught a bunch of tricks for multiplying and dividing. I know this. I'm not a giant fan of those because I watch you guys struggle to go through your memory to find the trick. Whereas if you had your times tables memorized, you wouldn't need any tricks. Do you understand what I'm saying? But you've been taught these tricks at the expense of memorizing your times tables because nobody wanted to make you feel bad if you were not as good at memorizing as the kid beside you. So as a result, you know all these little tricks. to find factors. Some of them are the one that we just said. If it ends in 0 or 5, what will it divide by? 5. If it ends in 0, 2, 4, 6, 8, what will it divide by? 2. Does anybody know the one for 3? If the digits add up to a number that divides by 3, the whole thing divides by 3. Right? So 126. 1 plus 2 plus 6 is 9. So 126 will divide by 3. If it divides by 2 and it divides by 3, it will divide by 6. Okay, there's one for 9 too. I can't remember what it is though. It has something to do with the digits, but I don't care. I know my times table, so I don't know the tricks. All right? You're going to be using a lot of division over the next little while. So those division rules, if you know them, use them. If you know your times tables, use that. That's even better. And when I say know your times tables, I don't mean this. What's 7 times 8? 56. I don't mean that. I mean what's 7 times 8. And by the time that comes out of my mouth, you've already said 56. That's knowing your times tables. Everybody cool? Yeah. All right.
But sometimes when someone's put on the spot,
I know. Oh, no, I know. I agree with you. When you're put on the spot, it's like that. But by the same token, if we were on the volleyball court and I spiked the ball right at your face, what would you do?
well, exactly.
You're on the spot. You know what to do, right? Why? Because you practice it and you know it to death. Yeah? Okay. So let's go on here. We are going to do the factor tree of these two numbers. All right? Now, remember, this first example I gave you, 18, Joseph started with 6 and 3. I started with 9 and 2. Did we end up at the same place? Yes. So does it matter what I start with here? Not at all.
7 times 8.
What would you use? What would you use?
6 times 9.
Some of you are going to say 6 times 9. That's cool. You could also do 3 and 18. You could also do 2 and 27. Oh, I should have done that in a different color. 2 and 27. Right? Now, if I follow the blue one down, do I keep going from both of these branches? Why? Why do I keep going from both of those branches? Pardon me? They both can be further divided. Neither one of them is a prime number, yes? So I would continue. What is 6?
3 times
2
2.
times 3. Are those both prime numbers? Every time you hit a prime number, I like to circle it. And then 9?
3 times 3.
3 times 3. Yeah? Now, if I went this way, would I stop at 3? Yes. What about 18?
No, you can divide.
No, what would that be?
6
We're going to do 9 and 2.
or 6 and 3.
Or I could have done 6 and 3. Right? 9 and 2. Am I going to stop anywhere there? On 2. But 9 is going to go to 3 and 3. And then I'm going to stop. Agreed?
Yeah.
And finally, I could do 54 and 27. 2 stops. What about 27? 9 times 3, I can stop there.
7, 9.
And 3 times 3, I can stop there. Is everybody cool? Everybody could have done any one of those colors, yes? Now, knowing what you know about exponents, what would you write down here if I told you I wanted the product of primes? Well, a product means I got to multiply factors together. And if it's a product of primes, it must mean I can only use primes. So how could I write 54 as a product of primes? 2 times 3 times 3 times 3. Yes? Now, knowing what you know about math, would a math guy write that? What would he write instead? 2 times 3 cubed. Is everybody good? Yeah? Did I write it?
Yes.
So do you write it? There you go. Everybody good? Now, I don't want to make it this messy over here. Okay? I don't. Because there's no need, is there? We ended up at the same spot. And you only could have done 227, 318, or 69. Yes? So over here, we're not going to do them all. We're just going to choose our first two. What should you start with? It ends in 2. What would be a good thing to use?
Divided by 2.
2. 81. Stop there. What's 81 break down into?
9 times 9.
9 and 9. Can't stop there. What's 9 break down into?
3 times 3.
3 times 3, 2 breaks. 3 times 3, 2 breaks. And what is our product of prime here? 2 times 3 times 3 times 3 times 3. Math guy wouldn't write it. 2 times 3 to the 4th. Does everybody understand the blue highlighting as of now? That is where you ended your previous use of factor trees, right? Most of you. I know this because my daughter is doing this right now in the 7th grade. Is everybody cool to there?
Yes.
All right, good. Now, like I said, there is a use for this. In grade 7, it ended here. If you could draw a factor tree, you got your gold star and you moved on, yes? There is a use for it. We're going to use them right now. Greatest common factor. I'm going to highlight that in yellow, and I'm going to write GCF. You already use GCF all the time. Here is when you use it. 6/54. Is that a fraction you would ever have left in Mrs. Bad Crumble's class? No. Why?
Because the bigger numbers in the rule.
Because they can be simplified.
It can be simplified. What would you simplify that to? 1/9. Why?
Because they both can be divided by 6.
They can both divide by 6. Yes? Because 1 times 6 is 6, 9 times 6 is 54. Yes? That is a greatest common factor. Okay? The biggest number that divides into both of the numbers that you're worried about. You already know what GCF is. You use it all the time. So, let's come back over here and let's talk about GCF with giant numbers. And these aren't even giant. So how do we find our GCF using prime factorization? Well, I have two numbers here, yes? I have 54 and 162, right? 54, I'm going to do in red. 54 was 2 times 3 times 3 times 3. I'm actually writing it out because I'm going somewhere with it. Math people wouldn't write 3 times 3 times 3, would they? They would do the 3 cubed. But for our purposes right now, I want to leave it as 3 times 3 times 3. Everybody okay? All right. 162, I'm going to draw in blue. 2 times 3 times 3 times 3 times 3. Yes? Now, greatest common factor. Is that 2 common? It's in both. So it's common. That's what common means. Is the 3 common?
Yes.
Is that 3 common? Is that 3 common? Is that 3 common? No. So the factors that are common are 2 times 3 times 3 times 3, right? What is 2 times 3 times 3 times 3? 54. So that means 54 is the greatest common factor. Now we check. Is 54 a factor of 54? Yes, because 1 times 54 is 54. Does 54 go into 162? Yes. 3 times 50 is 150. 3 times 4 is 12. 150 and 12 is 162. Is everybody cool? Yes? We're all good? Okay. So now, in your own words, you don't need to write it down, but in your own words, think for a second about what we did there. Does everybody have an idea in your heads to explain it in your own brain? Yeah? Anyone want to share what they are saying to themselves? I have to ask this because I have been giving the definition for finding common factors for 20 years, and still it does not get to every kid. So if you don't want to share it, that's fine, but you need to know what we did there. Do you know in your head what we did here?
Can you do that without writing it out like that?
What do you mean? Like, I'm going to write it in a sentence over here. I'm going to say what we did.
Okay.
This is what we did in this
Would I do
case.
that in my head though? Or would I have
No.
to write it out?
You don't have to do it in your head. You would write it out. You would do a factor tree and do this. But I need you to understand what we did here to get to 54. Does everybody get it?
Yeah.
So, all right? You list all of them, and you keep all of them that are common to both. All that are common to both. Does everybody understand? That's why I stopped here. Everybody cool? Now, what if I added What if I added 90 to this list? What would I need to do with 90? I'd have to factor tree 90, wouldn't I? Well, let's do so. 90. What's the first one you're going to use? 9 and 10. 3, 3, blank, blank. 2, 5, circle, circle. List 2 times 3 times 3 times 5. What's common to all three? 2, 3, 3, right?
5 and 3 are not.
So these are not common, yes? So if I add 90 to this list, it's only 2 times 3. It's only 2 times 3 times 3, right? Which is 18. Does everybody understand?
Yes.
Everybody? Because 5 was not common to all three of them, and 3 was not common to all three of them, we leave them out. Is everybody good? Awesome. Possums. Okay. Lowest common multiple. Oh, we never defined GCF. GCF is the largest factor of the group. Now, in pink, I'm going to write something different here. GCFs are less than or equal to the lowest number of the group. Everybody understand what I mean? Because our GCF was 54. Is that less than or equal to 54? Equal to. So it's okay. Everybody understand?
So you used the 90,
90 was just an example to make sure you understood this. Right? I listed the factors just like I did for the first two. Then I checked what was common.
and you used the top numbers.
You use any number that is common to all of them. Okay, I had to stop here because 3, 3 wasn't common to all, 5 wasn't common to all, and that 3 wasn't common to all. Okay? All right. LCM. Those LCM. You also use LCM all the time, but you give it a different name. 1/3 plus 2/5. How do you do that? you need a common denominator, which is what? 15. And that common denominator we call the lowest common denominator. But the lowest common denominator is really a lowest common multiple, because 15 divides by 3 and 15 divides by 5. 3, 6, 9, 12, 15. 5, 10, 15. The first number that's the same in both is the lowest common multiple. Everybody cool? Easy to do with little numbers. Harder to do with bigger numbers. But guess what? We get a trick. Lowest common multiple is the lowest number that your group is a factor. Now, the LCM can be found using prime factorization the exact same way. Well, no, what am I saying? It can be used, prime factorization can find the lowest common multiple. Similarly to what we did before. We list them all. Step 1 is list them. So 54 is 2 times 3 times 3 times 3. 162 is 2 times 3 times 3 times 3 times 3. Right? Now in factors, we only sought what was common. In LCM, we count every factor only once. And here is what I mean. Is 2 a factor of both of them? Yeah. It's in both, so we only counted how many times? Once. Is 3 in both? So we counted how many times? Once. Is that 3 in both? Yeah. So we counted how many times? Once. Is that 3 in both? So we counted how many times? Once. And then, because I have to count every factor once, do I also count that 3? Yes. So I counted that 2 once. 2. I don't want to use red. I counted that 2 once. That 3 once. That 3 once, that 3 once, and that 3. 2 times 3 times 3 times 3 is 162. Is that right? Is 162 times 1 162? Yes. So 162 is a multiple of 162, yes? And 54 times 3 is 162. So it's also a multiple of 162. Everybody good? And in pink is how I write this little reminder. LCMs are greater than or equal to the biggest number of your set. So now, what was the number I added to the first set? 90, right? 90 we broke down into 2 times 3 times 3 times 5, correct? Everyone agree? Okay. So count everything once. Do I count that 2 once? Is it in everything? So we count it once. 2. Is that 3 in everything? Yeah. So we count it once. 3. Yeah. Is that 3 in everything? So we count it once. 3. Yeah. Now, this 3 we have to count how many times? Once. This, because we have to count every number once. We don't count a repeat twice. Do I count this 3? Yes. And then I got to count that 5, because I count everything once. So the LCM, when I added 90 to the mix, is now 2 times 3 times 3 times 3 times 3 times 5. So it'll be 162 times 5. Everybody with me? Which would be 500, or 160 times 5 is 800, 810.
So what does that make it?
I just told you what it makes it, 810. The lowest common multiple of 90, 54, and 162 is 810. Everybody cool? Yeah? Now, we've already done the last step, finding the LCM and GCF. Is everyone good? All right, turn the page over. You guys do these, but I'm going to add one here. I'm going to add and 96. No. $133. That's what I'm going to add. Everybody good? So how do we start? We have to do factor trees. That is where it's going to end, isn't it? Because everybody's first branch of their factor tree might be different, yes? So the only thing that's the same is how we start. We'll do this one together, and then I'll let you go. Because GCF is easy. Nobody has problems with that. LCM blows your minds. I don't know why. 36. Everybody factor tree. I don't care how you do it. Okay? I'm going to do one that none of you will choose. Huh? I know, right?
Why not 6 times 6?
Most of you did 6 times 6 or 9 times 4.
That's what
I guarantee it. A couple of you might have done 3 times 12. I think, if maybe lucky, one of you did 18 and 2. So I keep going. 6 and 3. I've stopped there. I've stopped there. And 3 and 2. And then I write it out as 2 squared times 3 squared. Yeah? No matter how you started your factor tree, it ended here. Yes? Excellent. Now I'm going to do that again over here with 120. I am betting almost all of you are going to go 12 and 10. That's cool. Nothing wrong with that. I'm going to go 3 and 40. Whoa. You so crazy. 2 and 20. 2 and 10. 2 and 5. And no matter how you started, you're going to end up with 2 cubed times 3 times 5. Now, what have I done differently on this page than I did on the previous page? I'm using... The factors don't matter. I wrote this differently, didn't I? When it was time to actually find the GCF and the LCM, I wrote it out long on the previous page, didn't I? That's so I could show you the highlighting. Look closely. GCF. I only need to count what's common to both. How many 2's are here? 2. How many 2's are here? 3. So how many 2's are common to both of them? 2 squared, yes? Is there 3's in both? How many 3's are in both? How many 3's are there? 1. How many 3's are there? So only 1 3 is common to both of them, correct? Times 3. Is there a 5 in both? So I stop. What is my GCF? 2 squared, which is?
Which is 4.
Times 3?
Is
12. Everybody good? Okay. Now, LCM, and like I say, this is the one that messes with you guys, and I don't really get why. Count everything once. If I count all 3 of these 2's, does that count those 2 2's?
Yes.
It will, won't it? These 3 will cover these 2, correct?
Yeah.
2 cubed times. Will these 2 3's cover this guy's 3's?
Yeah.
Yeah, because there's 2 up there. I only need to account for 1 down here, right?
Yes.
Everybody with me?
Is it easier?
So it's 3 squared. And I got to count the 5 because I got to count everything once, correct? Times 5. What's 2 cubed? 8. What's 3 squared? 9. What's 8 times 9? 72. 72 times 5? 360. And then I check. Well, 120 obviously goes into 360 because 12 times 3 is 36 with a 0. 336 obviously goes into 360 because 36 times 10. And I'm good. I'm done. Is everybody cool? Now, do I care if you want to write these all the way out? If you find this easier, do it. If you find using the exponents easier, do it. I don't know which way you prefer. If you are from another country and you've been given a third way to do this, do I care? No, I just don't know what that third way is. Because these are the only ways I know how to do this. Everybody cool? Now, I did notice my daughter got this weird Venn diagram thing with 36 and 18 here. And she had to do, I could barely wrap my mind around it.
You're like this.
I could barely, why would you ever do that? I am not a fan of showing you something new when there's something that works perfectly well for 99% of the people. Do you understand what I'm saying? The 1% of the people that don't get this, if you come to me and say you can't do it, I'll work with you to figure out a new way to do it. But I don't like showing something completely different when 90% of you get this, and then that completely different way messes you up. Understand what I'm saying?
Yeah.
So if you are uncomfortable with factor trees and you don't want to say it out loud right now, what must you do? Come and see me privately. Okay? But I guarantee you, factor trees work wonderfully. You just need to practice a bit. Now let's say, well, Mr. Mars, I'm so bad at dividing and multiplying in my head. Use it.
Yay.
You may work together. You need not work by yourself. Do 18 and 24. How long will this take, do you think?
About like.
Just to do B.
Like
2 minutes?
2 minutes. Well, yikes.
Okay, see if you can get B done in 2 minutes. Some of you have already done it. Yes.
I have a question for this one. So is GVF, so it's 2 and then 2 power.
Only 1, 2.
Only.
You can only count 1, 2.
So it's like 2 and then
And how many 3s can you count?
3 square and then 3 is 1.
Only 1, 3. Yep. Indeed.
Ooh, okay. Yeah, I see what that for a second. How would I do this if there's like a 3 over a 2? If I was to get the greatest common.
Again, you count everything that is common to both.
So that's just, so there's 2 and 2, so that's.
And then?
Those are.
No, but look at the very end of both rows. Isn't there the 1 3 in both? So you count it.
Okay.
Dan, I'm about to go over.
Oh. No.
But I'm more than willing to talk to you right now. It's up to you.
So for the LCM,
Count everything once.
not everything one. So it's
2 cubed, 3 squared. Yep.
2 dish, and then
Yep.
3 cubes.
Yep.
3 squared.
All right. 18.
6 times 3.
We already have done 18. So it is 2 times 3 squared. Yes? 24. 2 and 12. 2 and 6. 2 and 3. So it is 2 cubed times 3. Yes? All right. GCF is everything common and only common. What helps you remember? On the first page, GCF has to be smaller than the smallest number, yes? So that means you can't count everything. You're going to get bigger, aren't you? You can only count the commons. How many 2's are in both of them? This guy has 1 to give. This guy has 3 to give. So the most we can get out from both of them is 2. Right? So my GCF is a single 2. How many 3's can this guy give? It says right there, 2 of them, yes? How many 3's can the blue guy give?
1.
1. What's the maximum amount of 3's you can take from either one of these guys? You can take, no, you can't take 2 because this guy only has 1 to give. Can only give 1, yes? So it is 2 times 3, which is 6. Does 6 go into 18?
Yes.
Yeah. Does 6 go into 24?
Yes.
Yeah. Good. LCM. Count everything once. Do all of this guy's 2's cover this guy?
Yeah.
Yeah, because he's got 3 to cover, so we can cover 3 2's, and there's only 1 there. So we cover the 3 2's because we count everything once. What about this guy? Does 18's 2 3's cover 24's 1 3?
Yeah.
Yep. So it's 3 squared. What's 2 cubed? 8. What's 3 squared? 9. What's 8 times 9? 72. Is everybody good? Great. Try the next one by yourself. Go.
Nine isn't a prime number.
No.
3 and 3. 3 squared by 5. 75. What is...
Chair aerobics. No, dude. 9 times 5 is 45. I got you, Gio. I got you.
There we go. Okay. 15. By 5. Stop there. 15 is not prime number, isn't it? 5 by 3. Hey, I got it. And then 5 squared. 5 squared. Okay. So that one has 2, and it gives it 1, so that's 3, and then it's equals 15. Ooh, I got it.
All right. Are you sure?
Yes.
Okay. What's going here?
3.
Yeah.
That was 5.
Yeah.
And that's 15.
Yeah. Because there's only 1 3 common to both and 1 5 common to both. What's the LCM?
3 squared.
3 squared times 5 squared, which is 9 times 25, which is 225. Yeah? Yeah. Now, D. Let's separate the wheat from the chaff. It's a farming saying. Wheat is what you want. Chaff is the garbage.
What's chaff?
Chaff is the stalk. Like wheat grows like grass, right? Up a plant and then the seeds are at the top. That's the part we want. This down here is garbage. It's called chaff. So when you are a farmer, you have to separate the wheat, what you want, from the chaff, what you don't. And it's a saying to separate the good people that really know what they're doing from the people that don't. So let us separate the wheat from the chaff.
So 35.
How many factor trees do I need?
3.
3. 35 is an easy one. What is it?
So you can do 6 times
5 and 7.
5 and 7.
7 times 4.
Done.
Oh, was it primers?
Yep. 84. 12 and 7. 3 and 4. 2 and 2. 133. 7 and 19. And they're both prime, aren't they? So, what's our GC? We have 5 times 7. We have 2 squared times 3 times 7. And we have 7 times 19. Please notice why I've set it up this way. What does that make it very easy to do? See the only thing that's common to all of them, which is what?
7.
So what's my GCF? 7. Because there's nothing to multiply it by. What is my LCM? Any other 2s? So do I have to count both of them?
Yeah.
Yeah.
2.
2 squared. Any other 3s? No, so I got to count it, don't I? Any other 5s?
Nope.
So I got to count it, don't I? How many 7s do I count?
1.
1. And then what? 19. Not doing that in your head. 4 times 3 is 12. 12 times 5 is 60. 60 times 7 is 420. 420 times 19 is 840 minus, 8,400 minus 420, which is 7980.
Why do you like your subtracting?
Yes.
Why?
Because up to here is 420, correct? 420 times 19. Well, 420 times 20 is 8,400, but I don't want 20. I want 19 of them, so I subtracted 420. 8,400 minus 4 is 8,000. 8,000 minus 20 is 7980.
Did you have to do that?
You can do any kind of multiplying you want. Some people like to multiply big numbers this way. 42 times 420 times 19, they like to do this. 420 and 0. And then down here, they like to go 10 and 9. 400 times 10 is easy. That's 4,000, right? 400 times 9 is easy. That's 3,600. 10 times 20 is 200. 10 times 0 is 0. 20 times 9 is 180. And then it's easy to add these up. 7,600, 7,800, 7,980. Some people like to do this area method. Some people like to do what I did. I do a mix. Is everybody good? All right, listen to me and listen to me closely. The next page is going to be weird. In the interest of saving paper, because these pages are related, I put them together. But this page, the right-hand side of it, page 147, is really part of tomorrow's work. So you only got to do 140 today. After tomorrow's lesson, you're going to do 147 and, a little bit more. Everybody cool? Sweet. Did I take your quiz score last day? I did not come around and get it? It is 9:09. I'm going to come around and get it now. It was out of 12 score.